Hello students, today in this lecture we will discuss about examples of chapter 2, that is lathe machine. Now in lathe machine we have discussed about a different equation. That equation may be of thread cutting mechanism, it may be of taper turning mechanism. So based on that there are chances of asking certain examples. So we will see all of them one by one, starting with First of all, as I have told you in our examples of chapter 1, first try to understand the given data in the example. Then let us understand that what they are asking in that example. And after that, using certain formula, solve the example. So now starting with our first example, the details given are: first, determine the cutting speed in machining a workpiece of 200 diameter. So first of all, what they have asked is we need to determine the cutting speed. So the final answer that they require, that is the cutting speed. So for that, given data is 200 mm diameter, that they have given the diameter of workpiece. Next, rotating speed of 100 rpm, that means they have given the value of n, that is 100 rpm. And they have also asked us calculate machining time if workpiece length is 0.5 meter and feed is 0.45 mm per revolution. So these are the other details given. So we need to find first cutting speed, then we need to find machining time. So now starting with writing our given data. So the given data, first of all, that is the diameter 200 mm and that is given is 100 rpm. Now workpiece length is given over here and that is 0.5 meter, but as we need to always use same unit throughout the example, so 0.5 meter we will convert it into the mm, and as 1 meter that is equal to 1000 mm. So over here 0.5 meter into 1000 that is equal to 500 mm. So we have converted that meter into the mm. And the last value that they have given, that is the feed, and feed is 0.45 mm per revolution. So these all are the details that are given. Now that they have asked us to find cutting speed. So for cutting speed, as we know, equation is cutting speed V velocity, that is equal to pi dn divided by 1000. So this is the equation, and for this equation keep in mind velocity will be always in meter per minute. Over here diameter, that will be always in mm, and this n, that will be always in rpm, that is revolution per minute. So these are the, for this particular equation, these are the standard units. I am repeating it again. Velocity is in meter per minute, diameter will be in mm, and n will be in revolution per minute. So now let us check. As diameter is in mm, okay, n available in rpm, so these two values are available. So from putting this value we will get the value of velocity, that is in meter per minute. So just put all these value available. Pi, that is the standard, that is 3.14, diameter given, that is 200, n is 100 rpm, and divided by 1000. So just solving this mathematical step you will get the value of velocity 62.83 meter per minute. So that is the first answer for the question to find this cutting speed. Now to solve the machining time, for machining time we have equation. Keep this equation in mind. Machining time T equal to capital L divided by F into N, where this capital L, that is equal to the workpiece length. This L indicates workpiece length, F indicates feed, and N indicates rpm. So over here this workpiece length will be in mm, feed will be in mm per revolution, and this n will be in revolution per minute. So now as you can see, we have available value of L, that is 500 mm, we have available value of feed and we also have available value of N. So just put these values in this equation. So as we put L, that is 500, feed, that is 0.45, and N, that is 100. So just solve this equation by using calculator and you will get the answer, that is 11.11 minutes. So that is nothing but the machining time. That means for this particular machining operation, for the length of component having 500 mm, it will take machining time nearly about 11.11 minute. So now using these two equation, first one velocity pi dn divided by 1000, this equation will be useful to find cutting speed, and this another equation that is useful to find value of the machining time. Over here keep it in mind, velocity that will be always in meter per minute, that we have indicated over here, and the tool life based on the given formula B1 condition, it is in minute. So these are the two values that we have found based on this equation. So I hope it is clear to you how to find cutting speed and machining time in the case of lathe machine. Now moving towards our next question, and this next question is based on to find, first let us read the details given. They have asked is calculate the change gears to cut a single start thread of 0.5 mm pitch on a center lathe having a lead screw of 1 mm pitch. So that they have asked is to find the change gears, that means gearing ratio which is required to obtain a desired pitch on the workpiece, and this we have discussed in our topic of thread cutting mechanism. So over here similar method, list given data. So over here they have given pitch required on the workpiece, that is 0.5 mm, pitch of lead screw, that is 1 mm, and now we have obtained this equation in our topic of thread cutting mechanism, that is driver teeth divided by D1 teeth equal to pitch on the workpiece divided by pitch of the lead screw, and we have value pitch of workpiece, that is 0.5, pitch of lead screw available, that is 1. So if we rewrite again, it is 5 divided by 10, and in fraction form it will be 1 divided by 2. And now keep this in mind, this is the required gearing ratio, that is driver by driven teeth must have the ratio of 1 divided by 2. So now if we consider gear having a 20 teeth, if driven gear has a teeth of 20, that means if we write for the case of the gearing ratio, so driver divided by driven, that is equal to 1 divided by 2 into, if we use one gear having 20 teeth, so another gear, that is the driven gear that we need to use, must have 40 teeth. Similarly you can also write another, such as if you select a gear having 25 teeth, then it must need to maintain the ratio, that means your ratio will be 25 divided by 50, because you are using the gear having 25 teeth. If one person want to select the gear having 30 teeth, then there is also no problem, just you need to maintain the gearing ratio, that is 1 divided by 2, and that is our answer. So over here this 1 by 2, that is the required gearing ratio, and based on the teeth, just take any one of the example having any number of teeth, and based on that write this gearing ratio equation. So this is your example based on the how you can calculate gearing ratio required for required pitch on the workpiece based on given pitch on the lead screw. So this is our second example based on the equation that we have studied in our theoretical topic. Now moving towards our third question, that is, just read over here. They have asked is determine the tailstock offset. So first they have asked is to find tailstock offset to turn the taper, and for this they have given 3 different situations, 1, 2 and 3, and keep it in mind over here I am saying it very clearly, never use the details given in condition 1 in condition 2 or 3, and don't overlap the given values in any of the condition. Use each and every individual condition and its given data, and use equation that is appropriate for that particular condition. So now starting with first condition they have given, that is 5 degree on a bar of a length 300 mm, means we need to find a tailstock offset required for the case of if we want to obtain 5 degree taper on a bar of length 300 mm. That means you can see over here alpha, that is 5 degree, length, that is 300 mm, and we need to find s, that is nothing but the offset distance. So now using this equation that we have obtained in our taper turning topic, tan alpha, that is equal to capital D minus small d divided by 2 into L. And as we know, capital D minus small d divided by 2, that is nothing but the offset distance. So we can write as S divided by L. So now our equation will be tan alpha equal to S divided by L. Now we have value of tan alpha is 5 degree equal to offset, that is S, we need to find, divided by L, and the value of L that is given over here, that is the 300 mm. So just tan 5 degree into 300, that will give us the required answer, and if we solve this you will get the answer, that is 26.24 mm. That means to obtain 5 degree taper on a bar of length 300 mm, the required offset on the lathe machine, that is the 26.24 mm. So this is our first answer. Now moving towards second condition, first see over here, in second condition they have given 20 mm to 30 mm on a job 200 mm long over its entire length. So keep it in mind, over here we need to find tailstock offset distance. For the case of to obtain the taper from 20 mm to 30 mm on a job of 200 mm long and over its entire length, means we need to provide the taper on its entire length. Over here capital D, that is 30 mm, small d, that is 20 mm, and capital L, that is 200 mm, but over here they have said that is its entire length, that means capital N and small l will be the similar. So this is the main important point to consider. Let us solve this. So for the second case, as you can see, capital D and small d and capital L, these are the given. But now as you can see, taper required is over its entire length, that means capital L and small l, these two are same. So now we will use the set over distance equation that we have studied. You can see over here set over distance, that is equal to capital L into capital D minus small d divided by 2 into L, and over here capital L, that is 200, small d 30, capital D 30, small d 20 divided by 2 into our small length, that is small length, that is the nothing but distance over which we need to provide the taper, and over here we need to provide a taper over its entire length, and entire length is nothing but 200 mm. So we will write it as 200 mm. So now just solving this equation you will get 10 divided by 2, that is equal to 5 mm. So this is the required offset for this second condition. Now we will solve our third condition. In the case of third condition, you can see over here they have given required taper is 20 mm to 30 mm over a length of 200 mm from one end on a job of 400 mm long. That means workpiece available is of 400 mm length, but the taper required is only on the length of 200 mm, and the diameter reduction that is required is small d is 20 mm and capital D, that is the 30 mm. So all the details are given that you can see over here. Capital D, small d, capital L, small l, capital L, that is the entire length of workpiece, and small l, that is the taper required on the given length. So now using the same equation, set over distance capital L into capital D minus small d divided by 2 into L. So now just put this value, capital L, that is 400, capital D, that is 30 minus 20 divided by 2 into small l, that is the tapered required, that is on 200 mm length. So that will be 200. So now our answer will be, if you solve, you will get the answer that is 10 mm. So the answer that is required, that is nothing but the 10 mm. So set over distance that is required for the third condition, that is 10 mm. So over here we have understood different conditions that they can ask in taper turning questions. So over here we have seen three different conditions, in which first they have given taper angle, in second condition they have given taper length that is similar to the entire length, and in third condition taper length and entire length are different, and based on that we need to find this set over distance. So these are the solutions for this different number of examples that they can ask, and you can try different number of examples also for the practice condition. Now up to now we have used different number of equation, that is based on the thread cutting condition, based on the machining time, based on cutting speed required, and different taper turning condition. So these all are different number of questions or examples that they can ask in exam. So in our next lecture onwards we will deal with different examples also. So looking forward to see you all in our next lectures. Up to then, thank you.